Thank you very much for Andy and Luca for giving me the opportunity to come here, both to hear all the great lectures and get a chance to share about my research. So this, in a lot of ways, will be a continuation of Matthias's talk yesterday about the construction of minimal surfaces in general using balance equations in the setting of doubly periodic minimal surfaces. So definition, and I'm working with minimal surfaces in R3, so minimal surface would be doubly periodic if it's linearly independent if it's invariant under two linearly independent translations. So this one is one of the oldest known minimal surfaces constructed by Shirk, I think in 1835. This would be just the fundamental domain of it, or looking at it in the quotient. One of the translations would be by that vector, the other one by that vector. And maybe just a note about I'll have a bunch of images in the talk. One note, so it looks like I'm cutting, the image is cut off here and up at the top as well. Those are actually the ends of the surface, so they would just continue down forever, these ones, and then the top ones continuing up forever. So this, we could consider this viewing the surface in its quotient space, the flat torus cross R. If we extend it out in one direction at one of the directions of the period vector, just doubling it up there, and then the other direction, most of my images will be showing two copies of each translation. Some properties of doubly periodic surfaces, if we let lambda be the group generated by the two translation vectors, and we take a doubly periodic minimal surface in R3 that's complete, properly embedded, then the quotient, modding out by the translation vectors, will give us a properly embedded minimal surface in the quotient space, T cross R. And work of Meeks and Rosenberg on doubly periodic minimal surfaces showed that the quotient will be diffeomorphic to a compact Riemann surface minus a finite number of punctures. The punctures in the quotient are going to correspond to what in the quotient would be the annular ends. And when you view the surface in R3, those would correspond to the half-planar ends. We'll assume in most cases when you see the images of doubly periodic surfaces, we'll assume that the period vectors are horizontal. And so the ends of the surface are going to always be going up and down. So for that reason, we'll refer to them as top and bottom ends. And the genus and number of ends of a doubly periodic surface, we'll always count them in the quotient space. So for example, doubly periodic, the Shirk surface, diffeomorphic to a four-punctured sphere, genus 0, and has four ends in the quotient. And the classification of doubly periodic surfaces, it fits into two categories. Our Shirk surface, you have the top and bottom ends are non-parallel. In this picture, the top and bottom ends are orthogonal to each other. The angle between the ends can vary between 0 and pi. All the ones that I've constructed have parallel top and bottom ends. And the first examples with parallel top and bottom ends is genus 1, and that's the three-dimensional family of surfaces that was constructed by Curvature and independently by Meeks and Rosenberg. This is one example of that, a surface in that family with assuming extra symmetries. And then the quotient of it. You can see the genus of the image here a little better than looking at the image in R3, giving us a closed cycle around that piece right there shows the genus pretty good. Another example within that same family is that one. And Wei in 1992 simply added a handle to that one to get a genus 2 example. And this one lies in a one-parameter family of minimal surfaces. And he used an application of the intermediate value theorem to prove the existence of this one-parameter family of surfaces. And so similar to his proof, at the ends, we would have the Gauss map G, either 1 or -1 at the ends. In order to control that, that's going to determine the location, say, of this point right here. And then we have two free variables just given by the location of those 2 points. Mean value theorem allowed us to solve, intermediate value theorems, allow us to solve for those two. An additional one with genus 2 was constructed by Rossmann, Thayer, and Wohlgemuth in 2000. Essentially, it just was the way picture had a handle right here. The Rossmann, Thayer, Wohlgemuth one added the handle here instead. And they also got a similar genus 3 example with arbitrary ends as well. And that's, up until now, that had been the extent of doubly periodic examples. Matthias and I, we proved this theorem that for any genus, g bigger than or equal to 1, any even number, and capital N bigger than or equal to 2, we'd get a corresponding three-dimensional family of doubly periodic embedded minimal surfaces with capital N top ends and bottom ends. This being an example of a genus 7 surface, and this being one slightly more complicated one of a genus 4 surface. We also got some other ones with more ends. So this being one, just viewing it in the quotient. So again, these pieces right here, they would actually extend down forever, and the same thing on the tops. And then, for example, this side right here would be identified with this side in the quotient. And then these necks would also be identified back with over here as well. So we could get any combinations like this. One neck between these two flat annuli, any number between these, and then alternating again, one neck here, and then any number here as well. Another type that we were able to get surface with this one example with 16 ends, but we could have any number, just a multiple of 4 on the ends. Just these ones just adding in one neck between each plane and then having any number of the necks here that would then be identified back in the quotient with this side. So, the idea behind constructing these was looking at one of the limits of the wave family, which this movie shows. As we approach the limit, wave surface limits in a foliation of R3 by parallel planes connected by tiny catenoidal shaped necks. Each one of these, so the necks just shrinking to points. So the limit surface would just be what we call a noded Riemann surface. And the location of the nodes, it turned out, satisfies a particular balance configuration or balance equation. In this setup, where I have the two necks that were coming out, a larger neck coming out this way, they formed an isosceles triangle. And the limit of the quotient being the disjoint union of two copies of complex plane minus the origin. So the idea was go in the reverse direction. Start with a noded Riemann surface, having the nodes satisfy a suitably non-degenerate balance equation or configuration, then open up the nodes to get a doubly periodic surface. So here was with this one, what it might look like when we open it up. Now this is giving, I have no idea, I haven't shown the existence of this, all of the ones in this video. This is going really far away from the limit because we're applying the implicit function theorem in a neighborhood of the limit to prove the existence of the surfaces. We don't know how large of this family actually exists yet. Okay, so again, this is using a technique developed by Trizet, and it's actually applying these surfaces. They have some similarities to the Riemann minimal examples, and Trizet, he developed his technique with that. So that was just Riemann's minimal example, just having planes with one neck in between each one. And then Trizet showed you could add extra handles between the levels. So our setup is pretty similar, except instead of planes, we have these flat annuli at each level. So near our limit, our candidate surfaces should look like a collection of flat annuli connected by tiny catenoidal shaped necks. In the limit surface, the necks should degenerate to points, like in the animation showed. The quotient limit should be a noded Riemann surface. Each component in that noded Riemann surface will be a twice punctured sphere with nodes on it. And the nodes, well, in order for this whole thing to work, need to satisfy some balance equations. So the idea is start with a finite collection of punctured spheres, with nodes such that the nodes satisfy a suitably non-degenerate balance configuration, then construct a family of Riemann surfaces in a neighborhood of the noded surface. So 5 minutes left? Okay. Then, on that whole neighborhood of that family of surfaces in the neighborhood of the noded limit, construct the Weierstrass data on each of these surfaces, kind of with an idea of what the Weierstrass data should be for the kind of surfaces we want. The nice thing is that our limit surfaces are just disjoint copies of Riemann spheres with two punctures on them in this case. So it's easy to solve the period problem for the Weierstrass data on each of those pieces. Okay, so solving the period problem at the limit. The trick is then to be able to apply the implicit function theorem in a neighborhood of the limit to solve the period problem in a neighborhood. Okay, now, so you've seen the Weierstrass data in general for some settings. Here's what it would look, the period problem would reduce to for my surfaces. So here's one where I have 4 levels, one neck going down, that would be identified up there, 2 necks between these 2 levels, 1, and then 3 necks. So just one specific example. So these cycles I have on here is just a basis for the homology for this particular example. So these cycles around the necks, there just intuitively we would want the period to be 0 there. So that's the first one, the equation up there, that real part of those integrals would all be 0. The next one, that period, the B11, is one that's giving me kind of my non-horizontal period. It should have some vertical component to it. So that second one equal to the tau 1, tau 2, and tau 3. Tau 3 definitely being non-zero. All of the examples pictures I have would be with the tau 1 and tau 2 equal to 0. That one, my vertical vector being, just being vertical. And then the third ones will be the cycles like going around this one and so on. So those ones I want to be closed cycles on my minimal surface as well. So that's why those ones 0. These last ones is giving me the other period of my surface. And that's just, I'm just placing the ends of my surface, the punctures in the domain space at 0 and infinity at each level. So integrating along those should give me the period of 2 pi plus or minus along those at the ends. Okay, so dealing with disjoint union of noded Riemann surfaces again, we can do complex analysis on these and compute the periods as residues. So the balance equations fall out of computing those residues of the cycles around those catenoidal shaped necks. And they're given by the following equations, a bit nasty looking. But actually when you sum all of them up, no matter what you plug in for the pKi's would just be the location of the nodes. Summing up these, no matter what the pKi's, it's just, the sum's going to be 0, and that's just by residue theorem. So we're just summing up the residues, essentially. So as I mentioned, the location of the nodes. If the location of the nodes provides a balanced configuration, that's when, by definition, those fKi's are all equal to 0 for each k and I. The location of nodes will provide a balanced configuration provided that the AKI periods are all 0 for the noded limit. Now the non-degeneracy of the balanced configuration, essentially what that is, we take a look at a map from the parameter space of the nodes, all these pKi's, so some vector p into the space of those force equations, some vector f. So you look at the differential of that. If that differential had maximal rank, couldn't have full rank because the sum of those forces is always equal to 0. If it has maximal rank, then we would say our balanced configuration is non-degenerate. And that's what is going to allow us to apply the implicit function theorem in a neighborhood of the limit. So giving us this theorem, which is essentially a building block for getting examples of doubly periodic minimal surfaces with this particular limiting behavior. Limiting as the foliation of R3 parallel planes with tiny catenoidal necks attached between the different levels. So this first parameter, the k, this k running from 1 to capital N, that's giving the levels, the number of levels. This parameter, the n I from 1 to n sub k, is the number of necks between, say, the ith level, the kth level, and the k plus 1 level. So given some non-degenerate balance configuration, we'll get three-dimensional family of surfaces with our desired properties with that particular genus and 2 times capital N horizontal ends. That's time. Can I take 2 seconds more or a little? Okay, so the simplest case, which is similar to the example Matthias gave, say one big neck going up and say n small n's going down. The force equations reduce to somewhat similar equations to what he had. Solutions to them are given by roots of these polynomials, these p sub n's. This being an example with the genus 8 example, roots of that polynomial. I'll also mention these examples like this, so I need to come up with non-degenerate balance configuration. Well, essentially what I'm going to take is, right here I have the 1, 2 set up, one neck going down, 2 going up, 1 here, 3 going up, identify with the back. Essentially, it's not too difficult to show that you can, given 2 balance configurations, like a 1, n and 1, m1, that you can inductively combine those to get a new non-degenerate balance configuration. Same deal with this one. I'm just combining 2 separate balance configurations as well. Probably you could get more complicated ones from this, but that's as far as we got before we wrote the paper. One last slide showing going up the wave surface approaching the other limit gives an idea of another possible gluing. Here we have, over here, kind of like a doubly periodic shirk, singly periodic in the middle, and another doubly periodic, giving an idea of possibly gluing together different types of pieces instead of just the planes and catenoids. This one's been a little more elusive to figure out how to do it, though, so that's a work in progress. Thank you.
Questions or comments? So you use the same technique for this as well?
Trying to. It's one of the differences is, like, if I tried just gluing together doubly periodic shirk with singly periodic in the middle, another doubly periodic in the end. There I'm gluing end to end, whereas with the previous examples I was gluing, like I had planes and I was just cutting out a piece, gluing and a catenoid into that. So I'm gluing in the end of the catenoid into the plane, but it's not quite an end-to-end construction. The problem is, as you approach the limit here, the singly periodic shirk surface, the ends on it, they're getting parallel to each other, and in that case, either you can scale so the singular periodic shirk is limit will be a catenoid, but then you end up just with 2 ends, and I need more ends to glue together because I'd need 2 on each side to glue to the doubly periodic shirks. So I need to figure out a more complicated gluing construction for this setup as a result.
In the number of Trézé's papers, he uses the Riemann bilinear relations in a important place. Does that show up in your work as well?
Actually, I'm not sure what the Riemann bilinear relations are.
That would be a no.
Then yes, they don't show. They must not show up.